Okay, so this little integral question turned out to be a really fun question for me to do. Um, it's not as hard as it looks on the onset. Okay, so we have this weird number, capital E, defined by this integral. Notice we don't have to evaluate this at any stage. It's just sort of defined as that. And we're actually asked to show that this other integral here can be written in terms of E, right? So I don't know about you, but for me, if you want to find one integral in terms of a very similar integral, the first thing I tried was integration by parts. But then I quickly realized that that's not going to work, as you might as well. So it's a good instinct to have to try parts by parts first. You might want to make that a u or a v dash or something, but you'll quickly find it doesn't work. So what's your second protocol here, like go to call? What are you gonna do now? Well, for me, I guess looking at this integral here, how could I incorporate the other integral in it, right? So this is x times that integral, and I guess the trick you have to spot here is that, well, simply you just want to expand it in this fashion. I spotted this trick, right? I'm not really sure how you would spot this trick. I don't even know how to describe like why I spotted it. That's the annoying thing. It's kind of like I wish I could like architect the logic behind it, but I guess I was just lucky. So I mean, expanding out the numerator and writing what are we doing here? We're using a neat trick. We're adding and subtracting the same thing. That's what I'm trying to say, right? So you can add and subtract the same term. That won't change anything. That's a really cool trick that you do in a lot of mathematics when you go to university and in STEP. So you add and subtract some convoluted thing, and in this case, we're actually adding and subtracting our number e, right? You see that we added it in here, and then we're subtracting it here as well. What that means is the integral just becomes, you see this, the denominator is now the same as the coefficient of e to the x. So actually that just becomes the integral of e to the x. Okay, and then of course this is just minus e. Because our limits matched up, so that was fine. So then the other thing is just calculating the integral of e to the x between 1 and 0. But that's pretty easy because we know that if you integrate e to the x, you just get e to the x. So that'll be e minus 1. And this bit is minus e. So that was the trick there. Really just writing the numerator, adding and subtracting, making the numerator the same as the denominator to cancel that fraction. Okay. So now for the step part, so we're going to take that and apply it to something a little bit trickier. So what could you do here using a similar idea? Well, if we have the integral from 1 to 0 of, this time it's x squared over x plus 1 e to the x dx, right? Well, what are you going to do differently? Well, it would be nice, I guess, if you applied the same trick and got a x plus 1 all squared on the top line, then an x plus 1 down there. Okay, you can do that. So the way to do that is what did you add in? What did you fix it with? Well, you added 2x and you added a 1 in order to complete the square. So I'm just going to take those guys away. Minus 2x and minus, I guess just minus 1. So minus, yeah, well, that's just going to be x over x plus 1. It's minus 2x over x plus 1 e to the x. Okay, but what's good about this is, what's good about this integral now, I guess I should, be a little bit better with my notation and write that dx in, but you'll see that this denominator cancels with this. We'll just have an x plus 1 times e to the x, which is good, because we can integrate x e to the x, and we can integrate e to the x. Okay, these are both standard integrals. You know, you do this one by parts. So standard C for integral. This one, well, I won't say too much about it. Then actually, good news. We already know what both of those are. We know that this guy's E, and we worked this out in the previous question. Okay, so actually applying that again wasn't that tricky. But we're about to enter dangerous territory now, because we now want to apply this idea to an unfamiliar context, which will push us a little bit. So we know how to integrate integrals of the form e to the x over 1 plus x. Well, we don't know how to integrate it, but at least we know it's defined as some number. Okay. I notice it is going to be a constant number, so whatever that curve happens to be, it's going to be e to the x, but it's going to be like stretched a little, right? So it's going to like maybe like that or something. So that number is just going to be exactly here, the area of that. So I don't know what that number is going to be. Maybe it's around 4 or 5, perhaps. Probably less than that. I don't know. I don't want to work it out. There's no point. So we know how to integrate it to that form. Well, I guess the natural thing to do here is say, well, you know, this number in the exponent, it'd be nice if that was just x. So I guess the natural thing to do is use substitution. I go 1 minus x over 1 plus x is u. Okay. And now the only thing we need to work out, well, what we should do right away is find du. Okay. So use the quotient rule to get du by dx. That seems to make sense. So it's I have a handy trick for remembering the quotient rule, right? You may think of it this way. So that's. I mean, let me just check I copied that correctly. Yeah. Okay. So the handy trick for remembering the quotient rule. Well, it's if we want to differentiate with respect to x, I say low d high, so low, and then differentiate high, minus 1, minus high, d low, over the square of what's below. Pretty neat, right? I love that rhyme. I was so happy when I saw it, right? So low d high minus high d low over the square of what's below. Okay, so that's just what that turns out to be. And let's simplify that a little bit. So it's minus 1 minus x minus 1 plus x. Great, so it's going to be minus 2 over 1 plus x all squared. So what am I substituting in? What am I substituting in? Well, it's dx, so I'm gonna change it into du, and I always remember that by okay, the du's kind of look like they're canceling, right? So I want dx by du, so I'll just flip that to get dx by du. I mean, usually if I have an integral, right, and the substitution is a little easier, like 2x is u, I might just differentiate implicitly on both sides, get 2 dx is du, and then, you know, I can sub in pretty easily without any problems. But here it's just it's a little confusing, so it's better to just take extra care, make sure you've got the right thing. So, you know, we definitely want dx by du. So that's gonna be minus 1 plus x all squared over 2. So I'm gonna substitute that in. Now something nice will happen, because when I do that, when I put that 1 plus x squared over 2 there, you see that'll cancel. Yeah, that'll cancel like that. And what we're left with is something in terms of x, and we don't really want x. We want u. Okay, so now we gotta find u again. That's okay. We can do that, I guess. So currently our integral becomes 1, 0 of e to the u times 1 plus x. Okay, du. Okay, and I'll just factor out that minus a half. Okay, yeah. I got confused for a little bit because I thought the x's should be a u, but they're not. Okay, that's fine. So really, what is x here? What is x in terms of u? And I used to know a quick way of getting u. I think it might be just, I think x might just be this, but I can't remember. So unfortunately, we will just have to do it the long way to expand it out. So that's 1 minus x, 1 plus x is u. So that's u upon x plus u, and then we're going to 1 minus u, and then we're going to have a u of x plus, what's it going to be? Plus x, and then, whoops, that's not what I wanted to do. I wanted to, oh no, it is, yeah, that's fine. Yeah, so it is, it's 1 minus u over 1 plus u. Okay, so that was well remembered. So yeah, we find x and we put it back in. So we see it's 1, it's just gonna be 1 plus 1 minus u over 1 plus u. Okay, I guess I might write that as I'll write the 1 as the same denominator, right? So I'll have 1 minus u over 1 plus u. And then the 1 will be 1 plus u over 1 plus u, right? And I end up getting exactly 2. If I bring that 2 out, I just get the minus sign again, the u's cancel, and the bottom line is exactly what it should be, and I have the original integral once more. Is there a faster way to do that? I don't really know. I feel like there was a faster way to do that first integral. Oh well, you can correct me if you will. Right. Let's go on to the harder bit. Yeah, sorry. So yeah, the first integral is done now because, well, you know, it's of the form now. Now we've changed it, so I think it should be negative e to the u, and this is gonna be e to the u over u plus 1 du, which is just minus e. I think that's what we have. That should make sense, right? It's negative though. Why is it negative? Why would that be the case? I don't really know. It's confusing. It's confusing me. I feel like it should be positive. I feel like I might have made an algebraic slip somewhere, but yeah. I'm just going to pretend like that didn't happen, and we're going to do the next bit. Okay, so the next bit is a little trickier. You notice the main difference here is that the limits are different, right? So we want them to be 1 and 0, but they're not, right? So that's kind of annoying. And again, the x squared suggests the substitution. I guess u is x squared. That would be a nice substitution. But what happens to these limits under the substitution? All right, so we have the limits x, u. We know that x is going to be root 2 and 1, so u is going to be 2 and 1. Now it would be really nice if we also took 1 away from those limits, right? Giving us 1 and 0. That would be nice, wouldn't it? That would be exactly what we wanted. So that's why you're more inclined to try that substitution. Don't go ahead and substitute in u as x squared, because, you know, then you have the limits 2 to 1, and we don't know anything about that integral, because remember, e was just a number defined by the integral between 1 and 0. So you sub that substitution in. The substitution is a bit easier to do. Du is 2x dx, right? So dx is du over 2x. All right, so dx is du over 2x, and I'm just going to substitute that in to this integral. So I just get straight away the limits changed 1 to 0 e to the u over 2x squared du. And what's x squared? X squared is u plus 1. So that is actually turning out to be a half of e. Okay. Let me just go check that other integral again. Yeah. I mean, I probably made a small slip there, but I didn't have enough time to redo the video, unfortunately. So I'll just put this one up anyway. And yeah, hopefully you guys can take something from this.